Okay, so the next speaker will be Briffa, and she will tell us about the power constraining parameter from teleparallel gravity.
Hello everyone. First of all, I'd like to thank the organizers for organizing such a great conference and for giving us the opportunity to share research here. By means of introduction, I'm Briffa and I'm from the University of Malta, and I'll be speaking a little bit about teleparallel gravity. So, just a brief overview of what I'll be going through. I'll be going through a little bit about the introduction and the motivation, which everyone knows, so I'll be quick about it. But it will give us enough momentum to give us the motivation of why use teleparallel gravity. And then I'll be picking up, so after I introduce what's modified gravity and the teleparallel framework, I'll be going through picking one of the models that we studied and check the results for those, and then we'll go through the conclusions of what happened. Is this a viable framework? So the non-CDM model has had astounding success in describing the universe. However, as technology keeps on advancing and we keep getting much better data, we keep having these inconsistencies, such as the dark matter, what is dark energy, and as has been mentioned throughout the conference, we've had these tensions. So there are, as we've heard throughout the conference, there are many possible solutions that we can have. We could go through early times or late times, but one of them is when we go beyond the GR models, and I'll be focusing on the modified and extended gravity models. So why? Why do we go for modified gravity? Some of the late-time reasons for modified gravity would be galactic dynamics, like the problem that we have with the flat rotation curve problem, or dark energy. So we introduce the late-time acceleration without actually introducing the cosmological constant. So the modified gravity landscape is huge. There are many options. We can go either to add a new field or change dimensions, but what I'll be focusing on is changing the geometry, and specifically I'll be focusing on teleparallel theories. So what is teleparallel theories? Everyone has heard the famous quote that space-time tells matter how to move and matter tells space-time how to curve. However, curvature is a property of the connection, not of space-time. So we know that curvature is, if you parallel transport a vector around the loop, we have the difference between the vector would be the curvature. However, we can think about torsion as the non-closure of a parallelogram. We can see the torsion, we can think about torsion as the non-closure of a parallelogram, and we can think about torsion as small tornadoes across the space-time. And you can see that through this figure here, where we can see that how torsion differs from curvature. So how does this work? So GR, we have the Leibniz-Vita connection, which is a curvature-full but a torsionless connection. But one application of teleparallel is TEGR, the teleparallel equivalent of general relativity, where instead of the Leibniz-Vita connection, we have the teleparallel connection, which is instead curvatureless but has torsion. And the difference would be that instead of the Ricci scalar, we will have something called the torsion scalar. How does that work in our action? The connection between the Ricci scalar and the torsion scalar is connected by a boundary term B. Okay, so this is the curvature-torsion relation. So when we go to the Einstein-Hilbert action, we can immediately make it as such as that the Ricci scalar goes to a T, and we have that this is our TEGR action. At the level of the field equations, these are equivalent, so these are dynamically equivalent. So if we think about it, I will be focusing, so we have GR and TEGR, which are equivalent, and we're talking about here, but I will be speaking into a more, inspired by F of R gravity, I will be speaking more about F of T gravities. So how does that work? We have our TEGR action, with the torsion scalar, which is related to the Hubble parameter, and we are going to generalize it to a model, to a generalized f, and that becomes an f of t, which we're going to open specifically as minus t plus a function of torsion. And if we take a flat FRLW metric, the Friedmann equations become as written up here. So, now, we choose 3 specific models in our paper. However, I'll be speaking mostly about the power law model, the f of t, the first one. And why we choose these models is specifically because they can easily reproduce the lambda CDM model. They have a natural cosmic acceleration without adding any other factors in it, and they are quite stable. So, if we start focusing by the power law model, we have the power law model is described with 2 constants. We have the alpha 1 in the beginning and then the p1 as a power law. Now, how can we, given that these are 2 constants, alpha 1 can be easily obtained. And to obtain alpha 1 so that we can minimize the number of parameters, we evaluate the Friedmann equation at current times and we obtain the equation, the second equation that we can see here. So then, we can easily obtain the Friedmann equation for the power law model, which is the third equation, and E is just reparameterization of h of z divided by h naught. So we have those, and we can see that we can constrain the parameters here would be h naught, omega matter, and the p factor here. Now, I've already mentioned that these models reproduce the lambda CDM model. If we take P1 as 0, we can easily obtain the lambda CDM model, and we can also get the GR limit by putting P1 as 1. So, how does the P factor affect our h of z? So this graph shows us here that h of z, we have the Hubble diagram of h of z versus z, and we have the different p's allowing us to see how this model, how the different p's will give us a different Hubble diagram. I don't think it shows a lot, but there is the lambda CDM model as well in it, so we have an idea of where we are with this model. So we go beyond that. We also see that f of t gravity leaves an imprint on the perturbative level, and the matter perturbation evolution equation would be something like this. But we have the effective gravitational constant, which is dependent on the f of t as well. It is actually dependent on the f with a derivative of the torsion scalar itself. And hence we can also constrain the f sigma 8 using RSD data. And that's exactly what we do here. I am showing a very similar plot to what we've shown before, where we have f sigma 8 with z, and we have the different pi's, like the different powers, showing us how this model will vary our f sigma 8. The G effective within this model is exactly what we have over here. So now we come to the CMC analysis. So we choose the cosmic chronometers, we choose Pantheon plus PAO data, and we also introduce the RSD data, and we obtain, we do different combinations of the data sets to obtain these plots. So, as we can see here, for example, that the Pantheon plus shoes and the RSD put the value of H naught onto the higher end of the spectrum, but that is expected given that the Pantheon plus is the highest value that we have, so we agree with these results as well. We also see that how H naught and P are varying with each other. We have a little bit of an anticorrelation, but that is more pronounced between the omega matter and the P1 values over here. Here are the more precise, the actual values and the exact values of the data. We also put in the AIC and BIC values, which are information criteria to give us the goodness of fit of the model. So it is the goodness of fit through the maximum likelihood versus the complexity of the model through the number of parameters in the model. So we have the values over here, but the values are not high, so it means that we are moving in the right direction in the sense that here lambda CDM is not extremely or strongly favored over this model, but we can't say more than that until now. So, we also put the, given that we have the S8 tension as well, we also managed to get the sigma 8 knot, so we can calculate the S8, and we see also how the S8 parameter varies with the P1, and there is an extreme anticorrelation here, so as P1 increases, S8 seems to decrease slightly. So, the next thing we did was we compared H0 with both the Planck values and the R22 values. Of course, we have 3 models here. I'm focusing on the power law model, but in our paper we also did the Linder model and the variant of the Linder model. So here we can see how this is affected, how our values are affected, and how we get the effect and the tension, how it is, what type of tension we have. We do that as well with the by comparing to the S8 values, both with the kids' values and with the Planck 18, and we see that the tension here is less, but we need more information, more than this. So until now we have constrained the parameters at late time and scalar, but now we need to go a step further. So that's what we do. We propagate, we also go into the tensor perturbation, and we use the reparametrization of the tensor perturbations in f of t by using the alpha m and alpha t, which are just reparameterizations of the normal tensor equation. And we have that alpha m would be, we set alpha t to 0 because that is the tensor excess speed, and alpha m is dependent on the f of t model. And for the parallel model, we obviously use this equation. So how does it work? As William, I think, introduced back on Tuesday, the presence of scalar perturbations are usually parameterized with the power laws, and we have the tensor to scalar ratio as well. So now, apart from the h dot omega method, the p and the sigma 8, we can also constrain the parameters for nt and the parameters of r. How do we do this? We do this using Horndeskian class. It's a high class, it's a version of class. And we implement these changes through the tensor perturbations, and we now can also constrain the parameters for nt and r. How do we do it? We use the late time data using cosmic chronometers, Pantheon plus, but now we use the DESI ones. And as the BB spectrum data, we use the BK14. And we have the results over here. We are consistent. If we focus a little bit more, we are consistent with what we had before, but now we have a value for R and a value for NT as well, which seem to be consistent with literature. However, we need to do further analysis with it to see where we're at. So, as a conclusion, we see that teleparallel cosmology is growing and maturing, and we've seen that it enabled us to investigate how certain cosmological parameters are altered in these different f of t forms. We've seen whether it is viable or not, whether we can consider it further, and given that it has up till now fared well with observational data and the lambda CDM cosmology, we are thinking about going into more of a general class and general cases rather than specifying a model, and maybe go into even a teleparallel Horndeskian. That's it from my end, and thank you for listening.
We have 10 minutes of questions, technically.
Can you take us back to the specific models you chose? Alpha 1, for example, and V1 in that power model, they are supposed to be dimensionless constant?
Yes.
Okay, then if you take us to the effective gravitational constant.
I'm thinking whether alpha 1 is a dimensionless constant. Yeah?
Yeah, it should be then ft should be dimensionless,
You, yes.
That doesn't look like that's okay. You like a model. If you go back to the next one, this one, then that will definitely alpha 1 and T1 are dimensionless, and
I'm not sure
the
about
gravitational constant will
I get
will not
what
have
you
the
mean.
dimension.
We checked the dimensions. I might not remember them right now, but yeah, I checked through them, and it should be like they match.
Okay, but in the statistical analysis he gave numerical values for this constant.
For which one? For which constant? Alpha 1?
Yeah.
Alpha 1 is fixed. The P1 is left.
As a number in the code.
The P1 is left as a variable, as a free parameter.
That should be dimensionless, yes.
Yeah.
And alpha 1? What?
Alpha 1 is constant. We obtain it from the Friedmann equations.
Okay.
Thank you very much for your nice presentation. I would like to elaborate a little bit about your statement that curvature is a property of the connection and not of space-time. What do you mean by this? Because
it's just that the fact that instead of the Levi-Civita connection, we're using a teleparallel connection. I don't have the equations here written down, but yeah, that's what I mean by that.
Because this space-time is a manifold equipped with a metric.
Yes.
And from the metric you obtain the connection.
Yes.
So why is there, what about your statement saying that it's not the same property? It was at the beginning of your talk.
So I'm not referring here to the going from the Levi-Civita connection to the teleparallel connection. But the metrics and everything else are...
I presume it's about the definition of the space-time.
Yes, exactly.
Thanks for your nice talk. So you talked about, for the gravitational waves, you talked about primordial waves, right? Okay, so have you looked at the astrophysical gravitational waves?
Not yet, no, not yet. But yeah, that's a long-term plan, we hope.
Right, thanks for the presentation. Well, you show various of cosmological standard parameters, how they would be predicted slightly different and how better or worse they provide fits. But that's of course, that's all fair and square. But of course, you know, it's all should be taken with the pinch of a salt because the big error bars, the analysis might be model dependent. So my question is something else. Do you have any kind of a smoking gun prediction for this theory that would clearly immediately will be detected, tell us that this is the f of t that we should be considering? I don't know, maybe in the universe, you exactly primordial nucleosynthesis, for example, and everything like that happens exactly the same if you change the structure of the space-time. I know it's not a simple question, but have you thought about any kind of smoking gun prediction for the f of t teleparallel theory?
Yeah, I get what you mean. Okay, so here we're specifying a model, so you know, we have its limitations, but that's why our sort of long-term plan would be to go for something more general and seeing if it all works out. That I guess. I know it doesn't answer your question, but I think it needs something more time to elaborate and think about it, I think.